and to share my my slides. Oh, let's see. Okay, we are recording, and now, as I said, I'm going to share my screen, and let's see. Okay, I'm here. So well, I'm trying to open as much as possible the file. Well, I've only prepared for today the part that has to do with spatial autocorrelation. If you remember, if we go to Moodle, I think that it is still as I wrote it in the beginning. Yeah, I changed the title in chapter 5 just to only to talk about this specific role of spatial dependence. But if you remember, we will see in the slide again of for the whole methodology, we could also analyze how spatial regimes or spatial heterogeneity has something to do, something to say in this evolution. So the co-evolution of spatial neighboring regions, and well, this is the LISA methods, and are the ones that I'm going to introduce here. So chapter 6 and 5 are going to be the same, but what we cannot I can't explain because I don't have enough time. Maybe next year I should explain or give my classes in more hours than only the ones that I have. This year I think this year I've taught 10 hours. Maybe I need more than 10 hours. But well, don't worry, because what I'm going to do is chapters 7 and 8 that they both have to do with this spatial regime disparities and how they also are affecting the coevolution of neighboring regions, and what is this GMA or the rank decomposition index. And my compromise is that I will prepare the slides and also the R file. If I will try to explain as best as good as possible the slides, just to give them to you. And if you want to apply these methods, well, I also recommend, of course, to read our paper, the paper that I wrote with Andrés Vallone, that is the main reference here. And also, Andrés wrote a paper with Professor Julie Legalo, another student, and I think that these two papers, the other student is Ayuba, Legalo, and Vallone, also written in 2020. These two papers are very important to understand these last chapters that are the ones that I'm not going to teach because I don't have enough time. But as I said, I will prepare for you the slides, and of course you don't have to do any assignment related to these chapters. Of course not. Just I will prepare the slides, and I will give you the R code just because perhaps you want to apply this methodology in future or during your internship. So who knows, sometime in your life. So this is why I will, when I do that, I will send you an email in a few days just to let you know, and you will be able to download the slides and the R code. Okay, so well, this is the part we are going to present today. So the old chapter 5 and chapter 6. That is the analysis of spatial dependence and the LISA methods. The LISA methods introduce, to some extent, or you can introduce spatial regimes also. So it's chapter 6 is like an intermediate chapter between spatial dependence and spatial heterogeneity or regimes. Well, so let's go. And we are now in chapter 5, the role of spatial autocorrelation in the analysis of distributional mobility with Markov chains. Well, so we are now in this last part, well, not all the items, but these 3 and 4 ones, the role of spatial dependence and the coevolution of spatial neighboring regions. And particularly, as you can see, in this part of the procedure. So the only part that I won't be able to explain to you during the classes are these 2 ones, so spatial regimes with city coevolution and cohesion among spatial regimes. So we have more or less covered all the methodological procedure. And well, regarding this topic we are going to present today, so first, as ever, why considering such techniques? Perhaps they are redundant. We are explaining more or less the same as we have explained the other days with, you remember, the kernels or with the Markov chains. Of course not. We have something that is very important here, spatial autocorrelation. So we're going to take into account explicitly and formally, as we normally do, we usually do with spatial autocorrelation, and introducing in this scope of the Markov chains. So perhaps you remember the first 2 days that we were looking at some papers, and they also used these methods, spatial autocorrelation, in different ways, very creative ways, just to see if being closer in spatial terms, no, in the territory, being closer to determined neighbors, if it is going to affect my evolution in the distribution of a variable. Well, this variable can be population, per capita income, pollution, or whatever other phenomenon that you can that can be you know, considered in this way, in this framework of the Markov chains. Well, the second step is properly the spatial Markov chains, and the third and the fourth they have to do with the Lisa Markov chain. So it's the idea of the quadrants of the Moran scatter plot and this local spatial autocorrelation. So I suppose that particularly the DASEE master students, they know what I'm referring to, that you have studied spatial autocorrelation effect, how we can deal with it, so the Moran side, the Moran's scatter plot, some basic tests, etc. This is why, well, I will explain this, of course, but you know, very quickly, not in depth. First, why considering spatial autocorrelation in Markov chains models? So the previous methods, as I said, they have not explicitly take into account the spatial dimension of intra-distributional mobility. So we know that, for instance, the cities in Chile, they can grow or not. Maybe they have lost population during this scope of 70 years, so almost a century, and they experienced the movements in this distribution, the population distribution. So the question here is if spatial dimensions in being closer to big cities or small towns, that if it has you know, some consequences statistically significant. Okay, this is the idea, for example, here with this example of population growth. As you know, cities may spread around neighboring areas, this kind of urban sprawl. This could be a metropolization process, or sometimes they experience a chronic depopulation evolution. Sometimes it happens in places that have lost a lot of economic activity for whatever reasons, and they are slowly but surely experiencing this kind of desertification in terms of population. So both situations would correspond to positive spatial autocorrelation, because it is more surrounded by more, or high surrounded by high, and low surrounded by low. So it's like going to a direction, or to up or to down, but they go together. Not only one city, but its corresponding neighbors, they can grow, or on the contrary, they can lose population. But of course, we could find negative spatial autocorrelation. Sometimes it's complicated, because negative spatial autocorrelation is something weird in social sciences, but you could, of course. It would imply a systematic dispersed polarization of large cities. So think about spots in the country of very big cities and a desert between or among them. This would be the idea of this polarization of certain very big cities, like regional capital, or capital cities at regional level, and you have the capital. Everybody went to the capital, and the villages are empty. This is what is happening. For instance, if you know Spain, this is what happens in certain parts of inland Spain, like the Castiles, the old, with the exception, of course, of Madrid, that is in the center. But around Madrid, it's like a desert. So outside the metropolitan area of Madrid, you will find this kind of negative spatial autocorrelation. These capital cities, like Valladolid, León, Burgos, and around these cities, a desert. So very, very small villages losing people every year. So of course you can find a spatial autocorrelation. So it's not so easy, but as I said the other day, it is very important that you can translate. So I have negative spatial autocorrelation. What does it mean to this phenomenon specifically? This was a big effort for Andres and for me to translate into this metropolization, this urban evolution, to translate into this phenomena that are taken into account in urban systems. And sometimes, this methodology is very, very rich, as you will see, very rich, and you can extract a lot of information. The thing is that, lucky of you, you will have the code. So for you, it's going to be very easy to extract the information. The point here is to sit down and think about these outcomes. This is, I think, the challenge in your case. To write an interesting paper, because this methodology is really very, very efficient to raise some information that is initially hidden or not so clear. And well, let's go ahead. Well, spatial Markov chains. Perhaps you remember this first paper of Serge Rey and some others. Also the paper written by Julie Legallot in 2004, the one that Julie and I wrote in 2008. We were talking about Markov chains, but the spatial Markov chains. What's that? Well, they provide insight into the role of spatial neighbor cities at the beginning of the transition, cities or wherever spatial units in general. So in the beginning of a transition, of a jump, as I say, for instance, in the case of Chilean case, from 1930 to 1940, this is a transition. From 1940 to 1950, this is another transition, okay? So at the beginning of transition, cities, they have neighbors. I don't know if the neighbors are very big ones, or large cities, or small towns, but they have neighbors. So to what extent these neighbors at the beginning of the transition, of this jump, so if they are affecting, and with what probability, to a particular spatial unit. So the transition of this city, of this spatial unit, in the distribution, population, or CO2 emissions, or whatever phenomenon we are analyzing, this transition, if they are conditioned by the variable value of its spatial neighbors in the preceding period. So neighbors in the past are affecting the transitions of a particular unit from the past to the future. Okay? This is the basic idea. So as noted in Ray, so you have here this, well, I think that these papers are crucial. I'm going to check if I've uploaded to Moodle. If not, I will do that. So because they are crucial, they are central to understand what we are saying. Of course, besides the papers I have recommended you, the one that I wrote with Andres, or the other one with Andres, Julie, and Kazuma Ayuba. It's the name of the other guy. And okay, in this case, this is the maximum likelihood estimator for the probability. But now we have something different. We have an L here. So an L, why an L? This L has to do with lag. So we are going now to compute probabilities, but considering that my neighbors, my spatial lags, are in different quantiles of in terms of a variable. For instance, in terms of population, I can, for instance, have very small towns in the first quintile, or very big metropolis in the fifth quintile. Okay, this is what you know is now taken into account. So now what we count is the number of cities or spatial units in that depart from state I, for instance, the first quintile, to state J, for instance, the second quintile, from T-1 to T, okay, and divided by the total of the row, for instance, and we will get this p hat, that is the estimator. But we are going to do that considering different spatial lags around each unit. So in the end, we will get to this situation. So as many Markov chains as classes of each unit's spatial neighbors. Okay, so we will see that, but this is this L. This L is connected with each of the L's here in capital letters. Well, they are the same. Okay. So this N, as I said, is the number of times a sample chain with a spatial lag in quartile or quantile in general, L, started in state I in period T and transition to state J in the next period, T+1. Okay. It's something similar. Let's go to this other slide. Maybe it is easier to understand. Well, for instance, here, what we do in this, let's see this first. So the upper left matrix. This first matrix is the matrix, the probability matrix for a city. I think that this is the example also for the Chilean cities. For a city of departing in the first quintile in terms of population in one period, and going to, for instance, the second quintile in the next decade. In our case, the next period was the next decade, 0.25. But this 0.25 is different than this 0.26, or different this 0.24. They are the same, from Q1 to Q2 in T to T plus 1 in T to T plus 1. So what is the difference? The difference is that in this case, I consider only the cases of these units, these cities, that in some moment, in some of these 1 or 2 or whatever of these decades, they had neighbors that were in average in this first quintile. So I consider to build this matrix only these units that once in one moment they had in average neighbors that were very small towns. So take into account only these cities that once in one moment in one of these decades, they had in average very small towns around. What happened? What was the the probability of jumping from 1 to 2, from 4 to 3, etc., or to staying? To staying in the main diagonal is not moving. Okay, and let's go to this lag 5. So this lag 5 is the contrary. Consider the towns or the cities that ever in along the decades they had in average big metropolises around. What happened to them? What was the probability of jumping from Q1 in a moment T to Q2 in T plus 1? Much higher. Oh, 60%. Nothing to do with this 0.25. Why? Because this jump is up. Okay? And it is easier or more likely to go up when my neighbors are also up, they are in the 5th quintile, than when my neighbors are very small, that they put you down easily. So it is not so easy for a city to grow when it is surrounded by small cities. They can, of course, yes, but it is not so easy, only 25, 26% of probability compared to this 60%. This is what the results are saying. And this is the way we should interpret these results. There is something interesting. So this path dependence, so if you remember, the path dependence is this concept in general Markov chains that is connected with the main diagonal. So the main diagonal is capturing the probability for a spatial unit, for a city, for instance, of staying in the same quantile than the one that in which it was in the previous moment of time. So if in T I am in the first quintile, the probability of remaining in this first quintile in T plus 1. And of course, a lot of socioeconomic phenomena exhibit a high path dependence. So it is much easier to remain or to stay, even considering 100 of years, a century, almost a century, then of course you can change and you can move. Well, it is not so easy. At least a jump that is only a first order jump from one moment to the next moment, okay? They are, in our case, 10 years, but in spite of that, in 10 years, it is not so easy for a city to escape from being small and going up, or to lose population in such a way that I being as a megalopolis and going down and converting in a large city only. That is, and this is this path dependence. In general, we can find this path dependence, but it is not so high in this case. If you remember how it was when the other day we look at the classical Markov chain, Markov chains, the transition matrix. If you remember how was this non-spatial, so current Markov transition matrix. So these main diagonals are more or less 0.7 or above, 0.8 or even 0.9. And sometimes we find this one here. So one is a kind of absorbing situation. So one means that it is not possible for a megalopolis ever, it is not possible ever in 70 years to go down, so to lose population in a way that they could go to lower quintiles, if they are surrounded by very small towns, and also if they are surroundings, of course, by very large towns, or even megalopolis too. And we find this absorbing situation almost in all the cases. Well, the only exception is when we are in the third quintile, around the median value. These are the values for when my neighbors are in the median value in terms of population. Well, sometimes if a big megalopolis were in such situation of having this kind of neighbors, maybe they lose some population, to leveling the situation in the urban area, and only with 2% probability they could have been smaller and went to the next class. Okay, the next class, in this case to the fourth quintile. Okay, well, this is the way you must interpret these results. So it could be a mess, but when you pay attention and look a little bit, you find here a lot of information, very rich information. If you know, particularly when you know a phenomenon, it can be very, very important, can give you a lot of information that I said it was previously, maybe it was hidden. And the most important thing, maybe this information is not hidden, but what you can do with this methodology is computing, putting a number, calculating the exact probability you can find for this or that situation. Maybe that something happens, but with what probability? This is the information that you can find here. You can quantify your outcomes. Okay. So, well, as I said, you can compute as many transition probability matrices as number of classes. For instance, if you have prepared the quintile discretization, you can compute, or you must compute, 5 transition probability matrices, one for these quintiles in your neighbors. Okay, so these L's here are the values of the neighbors in a first moment of time. Okay, and well, this is the first one. So what I did is extracting this first one with small towns around, and the probability of jumping or going up or down in the distribution along this period of time of 70 years in Chile. I think that I have explained almost everything. Well, just interpreting this 0.24 again. So we are in Q2 in T and go to Q3 in T plus 1. So a spatial unit with a value in a variable X located in the second quintile in time T will move up to the third quintile of this X variable in time T minus 1 with a probability of 24.29%. When its spatial neighbors got in time T an averaged value of X placed in the first quintile. So when they are very small towns, the probability of being, a small or a town to be a city is 24%. So if you remember, I gave some names. So this Q1 was the small towns, Q2 were the towns, Q3 were the cities, Q4 large cities, and Q5 megalopolis. Okay, and this is what I was saying previously about this absorbing situation, absorbing state. In these cases, what it is happening is that distributional movements in the group of units with large values, so in this case it's with large values, is null. Is null independently of their spatial neighbors. And in this case, it is null even if, well, when the neighbors are small, but as we could see here, this situation repeats almost in all the cases, with the exception of the median, but it is almost one. So independently on the spatial neighbors, the megalopolis in Chile went on being megalopolis. So if they were megalopolis in a first moment, they went on being megalopolis in the next decade or the next period, no matter the size of their neighbors. So it is also interesting because, of course, they experienced the kind of urban sprawl, but this sprawl wasn't enough maybe to lose population as to convert into smaller cities. No, they stayed as very big megalopolis. And well, this was what I tried you to show. So these probabilities are the probabilities of starting in Q2 and ending, starting in one period in Q2 and ending in the next period in Q3. And if you see, depending on the spatial neighbors, if a city or a spatial unit has neighbors that are in the first quintile, that are small in terms of population or have less income per capita or whatever, the probability of jumping up, going to 2 to 3, grows with the spatial neighbors size. In this case, if we are considering population and cities, so it is not the same having small cities around that having very large megalopolis. That is the case. So towns will have more probability of become in the next period become cities when they are surrounded by megalopolis. So perhaps it is logical. You will see what you are saying, very normal things. So maybe it is what we expected at first. Yes, but we didn't know with what probability. So it is almost 70%. So it is interesting to compute or to get the exact value and to see how this probability grows with the neighbor size. Well, and in our case, well, just to say more or less what I have said, since we were analyzing cities, so urban areas in Chile, what we could see from these results in the previous slide is that cities tend to move up or down in the population hierarchy, where their corresponding city neighbors are on average larger or smaller. So it is not indifferent. So it is affecting in general. Well, in the case of megalopolis, no, but we could see that spatial dependence was generally significant in general terms, okay? Which could be evidence of the existence of positive spatial autocorrelation. So what we can see in Chile is that in general terms, if a city or a location is surrounded by, or a large location is surrounded by large locations, the probability of going up in the hierarchy is higher. And if a small town is surrounded by small towns, the probability of going down in the hierarchy is also high. So high with high, low with low. And this is positive spatial autocorrelation. So in terms of urban economics, what we have here is that bigger Chilean cities are likely to agglomerate. and to promote growth in their neighborhood, while the smaller peripheral ones suffer from endemic shrinking processes, inducing growth inequalities. So we have very spaces with high population, large cities, so very populated areas, joined to some others that are depopulating, but not this kind of, as I said, for Spain, this situation with isolated hot spots. So with very big cities surrounded by deserts. No, we have deserts joined to highly populated areas, big areas. This is what predominates in Chile. And of course, it is important to to pay attention to this absorbing state, in particularly in for the first, but not only for the first, only almost for all of the spatial lags. And well, this situation also takes place in large cities that are neighbored by the small ones. So the smallest and largest cities are not affected in terms of population size by neighbor city size. You see, this is more or less what happens. So here we have that. Let's see. Well, it is not exactly the same for staying in one. No, it's this. I think that this conclusion is not very well. I will change. This one only is present from Q5 first to Q5, not in Q1. In Q1, well, the probability is high. Of course, remaining in Q1, being a small town, the probability is higher if they are surrounded by small towns, but they are much smaller. Only 26, 27% of remaining being a small town if they are surrounded by megalopolis. So this is incorrect. I will change in the next version of the slide, sorry. And so this absorbing state is only very important, and something that you must pay attention. So the question here is, which are these megalopolis in Chile? Maybe the megalopolis are only a few enclaves, not a lot of cities in the countries, and perhaps they are not a high number of urban areas, and we could analyze one by one, maybe. It is not like in the rest of the groups. So we are talking about neighbors, but we didn't say anything about the spatial weights matrix. So the spatial weights matrix, it's a main tool to know the neighbors' values. So the neighbors, I said in average, because the neighbors are, if I'm considering city size, so it is the averaged city size around one city. So if it is an average, it is because I've considered all the enclaves that are around or neighboring one location, and the question is which are my neighbors. This is the main issue here. So as I said, it is important to compute the spatial lags, and we will need, as ever, the spatial weight matrix to capture this potential spatial interaction. In fact, what we are considering are not, the buildings or the trees or, the cars stopped in somewhere. No, we are considering people moving and commuting and interacting. This is what makes that a city grows or shrinks or whatever phenomenon they can experience. So this spatial interaction that happens among the spatial units in a system can be absorbed. Well, it is not the only way, of course, of considering neighboring values, but this is a main tool for spatial econometrics, as you must know. It is an n by n matrix, also here, for being n, the total number of spatial units. In our case, the total number of spatial units were the total rows in the Excel or the total number of cities in Chile, okay? If you have an Excel file, these are the units. The units are not the states, so this is a bit complicated. So the units are the cities or the regions or the spatial units, as I say. The main diagonal elements, as you know, of this W matrix is set to 0 by definition or by convention. Why? Because so this matrix considers, as you can see, the spatial units, so the cities among themselves, or the regions or whatever. So why these main diagonal elements are set to 0? Because by convention we consider that a spatial unit cannot be its own neighbor. Okay, so this is why we set 0 there, as we set a 0 for non-neighbors units and a 1 for the neighboring ones. So the rest of non-zero cells, they are capturing the degree of spatial dependence among the observations. So the degree of spatial interaction. As you know, many times we set only ones and zeros. So you are my neighbor, and no matter if you are very, very neighbor or only a neighbor, and you are not my neighbor. Well, sometimes, and many, many, many times, these spatial weight matrix work very well. So they are not so nonsense as many people says. They are capturing a high amount of neighborness, neighborhood, or this phenomenon of considering neighbors. But as you know, sometimes it is not the best way of measuring this neighborhood around one unit. This is why this W matrix can introduce some other definitions. Okay, and as you know, maybe there is a rich variety of way of specifying the structure of these weights. Well, I've presented here only some of them. They are not, of course, the only ones, but as I said, the first ones are the contiguity-based matrices. So the contiguity-based matrices are the ones that have a common border, these binary 0 ones, okay? But there are some others, as I said, that consider distance-based. So, of course, you are my neighbor, but this other unit is more neighbor to me because it is closer in distance terms. So the question here is, what is distance? So because we can think about distance in a straight line, the Euclidean distance, okay? Some others consider the arc distance. So in our case for Chile, if you remember, Chile is a very long country. And it more or less starts, well, not in the equator, but in one of the tropics, and almost finishes in the South Pole. So with such an extension, though it is very thin, okay, it is correct, it is thin, but very long. So we consider the arc distance. So the arc distance, sometimes it is very similar to the Euclidean one, but the arc distance consider that the Earth is spheric, and it's the distance measured as an arc. And in sometimes, if you, for instance, are working with European regions, so I recommend using the arc distance. If you are considering in the city of Paris or the city of Madrid or Santiago, specific locations, and this is your sample, the Euclidean distance is going to be more or less the same as the arc distance, okay? And, you are not going to find a lot of differences. And what kind of matrices? Well, there are some kind of distance band. So I identify a band. A band is a radius around me. Sometimes you know this critical distance. You know that farther than X kilometers or wherever, it's impossible to consider neighbor to some locations. So my neighbors are only inside a radius. This is a critical distance cutoff, And you can consider that the elements that are inside gets the value 1 because they are my neighbors, and the ones that are outside, they will get the value 0. You also could consider based on distance, but the k nearest neighbors. So why they are based on distance? Because nearest is connected with distance. Why you are nearest than other one? Because you are closer. So the k nearest neighbors can be 4 nearest neighbors, 5 nearest neighbors, etc. And the same, I can give them a value 1 to the 4th nearest one, 1, and the rest 0. You can be finer, of course. Sometimes you can combine these inverse distance weights, that is more or less a gravitational expression based on the gravity model, because we set this weight as the inverse of the distance, a square distance or only distance. It depends on the importance that you can give to this distance among units. And some people, what did they do, or they prefer, it was our case. We combined the inverse distance weights with the distance band. So in order to not compute, sometimes it doesn't matter, because if two units are very far one from other, this inverse distance will tend to 0, okay? But some others, it is preferable. If you know that farther than 200 kilometers, you cannot consider a city as neighbor to someone. So forget about considering it. But it is not the same being at 70 kilometers that being at 20 kilometers. So this is why I can combine these inverse distance weights with the distance band weights. So in R, in Geoda, you can find, of course, the way of combining. And the same with the k nearest neighbors. So the k nearest neighbors, why giving 1 to a nearest neighbor when perhaps, I don't know, this nearest neighbor, if I consider the centroid, think about the nearest neighbors to the centroid of Russia, the country, Russia, or the centroid of China. They are so huge that the nearest neighbor is very, very far. If you consider, for instance, the centroid of Switzerland and the nearest neighbor that perhaps it's in Austria or whatever European country. This is why many people say, well, okay, I consider the k nearest neighbor, 4, 5, 6, whatever nearest neighbors, but I combine this expression with the inverse distance weights, just to, to consider that they are neighbors and neighbors. Well, the kernel matrices are more complex. They are used in some software, particularly to test for certain misspecification problems in spatial models, like when you have a kind of group-wise heteroscedasticity and something like that. It's a kind of spatial regimes, but in the error terms, and it's a different concept. It is not heteroscedasticity, but group-wise. And in this case, it is recommended to use not only the classical weight matrices, but these ones. The geographers like to use this kind of, of neighbors that are based on frontiers. The frontier longitude, sometimes if you are analyzing a kind of natural phenomenon, like, I don't know, pollution or whatever, it is not the same having a very long frontier longitude that only have a very short frontier longitude. In terms of, I don't know, a pandemic. If, people in one of my neighbors, they are getting infected. For instance, if we have that people in, I don't know, in France, I'm not sure, they are going up in infections, and we share with France a very long frontier that we share a long frontier. The problem is that we have the mountains, the Pyrenees. So, okay, it is not the same sharing a long frontier that sharing a very short one. So sometimes this longitude of frontier could be interesting too. So it is curious, but in economics, it is not always important. As I say, perhaps you can share only a point with one province, but if a road or a railroad goes just crosses along this point, these provinces are going to be highly connected, even if they only share one point. So in economics, it is not the same. This is why in economics, we use this kind of accessibility matrices that are based on networks. Even they are now on fashion, using a kind of economic or technological distance matrices like trade flows. So they are going to be a different kind of weight matrices, because they are not based on physical or geographical distance. They are based on economic distance. And perhaps, I don't know if you have studied enough spatial econometrics as to know that you must be careful when using these economic matrices as W matrices, because you could be introducing in the right-hand side of the equation some endogeneity or connection with simultaneity with the endogenous variable. So this is why many referees, when we publish papers from the economics area, as it is my case, for instance, if I use economic matrices, they are going to say, oh no, I don't like that, because blah, 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 you will have endogeneity and it is a mess. Many people in economics says that if you don't use economic matrices, you cannot express correctly neighborhood connections. Well, I wouldn't be so sure. Sometimes pure physical weight matrices could be enough, because what you do in the models, at least in classical econometric models, is absorbing connections or relationships between variables in average. And if you want to absorb or to quantify the effect of vicinity as a variable, in general terms, be sure that using physical measures could be enough. At least you are absorbing 80% or a lot of this vicinity. Because with some exceptions, that of course you can find exceptions, vicinity, physical distance is very important. Well, perhaps with internet you will see we can, I am not in Dijon and I'm teaching here from Madrid. Okay, yes, you're right. But in very general terms, excluding some exceptions, physical distance, even this straight line, Euclidean distances that could be very simple and are not, very interesting for economists, but they could work in a special econometric model. So I'm not so uncomfort using these distance-based or contiguity-based matrices, in spite of being an economist, but because I am a professor of economics, of econometrics, okay? But of course, if you don't need to use, okay, pay attention, if you don't need to use the special weight matrix in models, in econometric models with a dependent variable, a y variable, x's, and an error term, as it is normal, it is the case here with the Markov chains. Maybe it could be interesting to try this economic-based distance matrices. In this framework, in the Markov chains, spatial Markov chains, I didn't do that, but I recommend you to try. Maybe you will find some deviations in some, I'm not sure, or not, or perhaps, as I said, you will be surprised of the performance of purely physical distance weight matrices. Okay, this is what I would like to say about these spatial weight matrices. As you know, this is the weaker part of spatial econometrics. Many people from economics or some other, areas, they don't like spatial econometrics because of these spatial weight matrices. Sometimes we also try to escape from them and use some other tool to represent vicinity, because yes, I agree that this is quite arbitrary. It is more or less arbitrary. You have to use something that represents vicinity. And why this matrix and not that other? Well, if you read Luc Anselen, he recommends to do some kind of robustness check. A robustness check here is using different specifications for the spatial weight matrix and be sure that they point out to the same conclusion. If you find very different conclusions with different spatial weight matrices, please go to the starting point, because maybe you have a kind of misspecification. What kind of misspecification? In the context of Markov chains, as we said the other day, one source of misspecification could be the way of discretizing a continuous variable. If you remember, we are discretizing in quintiles, but why in quintiles or not in quartiles or sextiles or septiles, natural breaks, cuts, or whatever other kind of discretizing a variable, okay? So maybe in this context we should, I didn't do that in R, but I've offered you some different specifications for the spatial weight matrices, and you can check the DSP package of Roger Vivand, because you will find a different kind of specifications for this spatial weight matrix, and maybe it would be interesting to try to apply these techniques that I'm showing you in this session, to apply the technique with using different types of different specifications for the spatial weight matrices, and being aware that you find the absorbing state for all them, if you have the same conclusions, or if conclusions change. So this is something that I recommend you to do if you want. It is not mandatory for the assignment, the next assignment, but it would be interesting, particularly if you are writing a paper. That I know that one or two of you are writing papers using this methodology, so it would be desirable to do some kind of robustness check, even if you put the results in an appendix or whatever. It could be interesting just to check for the robustness of the discretization, that is other source of arbitrariness. Okay. Well, here in the spatial Markov chains, we have also the test for spatial homogeneity. Why? Because it is important to check the influence of a space. So perhaps you say, well, here it is very clear with these cases or some other cases, but yes, it is clear, but you are not computing with a test. So this clearness maybe is not so clear. Okay, this is why we have the tests, the statistical tests, just not to rely on your eyes or your way of looking at results, but to take into account the statistics and levels of confidence. And this is what we do do here. So we have for this test a Pearson's Q test and the likelihood ratio test. As far as I know, these tests are presented in the Bickenbach and Bode paper. I referred to this paper the other day. They had this test on homogeneity, but time homogeneity, to analyze if you had some kind of structural change, two subperiods. And what we are doing now here is looking at the neighbors. It is not a spatial regime. So this test is looking at, so like two variables, the variable of the cities, with their populations, in our example for cities, and another variable that is for each city, it's a spatial neighbors, the value of population, and to see if there are a kind of concordance. This is more or less what we are doing here. The null hypothesis, as almost ever when dealing with special effects, is independence. So no connection or no spatial autocorrelation. Even like in time series, if you use the Durbin-Watson or some other tests, so it's absence of autocorrelation. Well, here is the same. It's a spatial independence. This is what we are analyzing. In spite of that, these authors gives us a warning. These tests are very asymptotic. What does it mean? So this means that you need a very high amount of the sample. So the sample size should be very large. Very, very large. So not big data, but more or less big data, okay? More or less. So what happens when you are working with a small sample? 100, 200 of units could be considered a small sample. More or less, yes, in terms of this test. This is why they gives us a warning saying that non-significant values of these tests must be interpreted with caution because these tests are too lenient, are too weak for small samples, and they what they say is that they stays in the null hypothesis with more probability than rejecting the null. So if you have a small sample, it is more frequent to non-reject the null, and doing that so like a type 2 error, so not being the truth. Okay, the truth. So if the correct outcome is reject the null because you have spatial dependence, if you have a small sample, be careful, because maybe you will tend to accept the null, and considering that you don't have a spatial dependence when you really has this effect. Okay, this is the point. When you work with tests, you cannot be like robots, like machines. You must study the test. You must have some information about the test, because every test in the world has weaknesses. Every. So you must more or less know the weakness of the test you are using, and evaluate if you can completely rely on it, or maybe complement this test with some other tests, or with exploratory analysis, or whatever other complementary measures. Okay, so sometimes you find the tests so automatically in the software that you don't stop and think about the test. The test is like, I don't know, God or an angel that comes from heaven to give you a message. No, no. Please be careful with the tests, because the tests can be sometimes misleading. If you don't have normality in the error terms, my God, a lot of people estimating by maximum likelihood, for instance. So maximum likelihood relies on normality. You know, it is the density function of a normal distribution, multivariate distribution. So, and you estimate by maximum likelihood, and you don't pay attention to the Jarque-Vera or some other test on normality. Please. Or you are using some test that relies strongly in normality. Be careful. Complement this test with some other measures, or be careful when you have to explain some results, because perhaps you cannot rely on them. So this is something that, so as ever, please stop. Please think about what you are doing, because now you have so easily the results. I'm going to show you a lot of results. Oh my God, this is a treasure. Yes, but you can die with the treasure, okay? Because sometimes you do not know how to interpret these results. This is what happens now with big data, open data, data. Please stop. Yesterday I was talking about smart data. We need smart data, good indicators, not only data, but useful data and useful tests. So be careful. And for instance, in our example here, well, I extracted these results from R. The results allows us to reject the null. We have these two tests. Well, these two tests are quite similar. They are not the same, of course. Sometimes it is interesting to use several tests if available, just to avoid some weaknesses. So perhaps if one test is weak and the other one is strong, so they can complement each other. Something that is very interesting of this test is that it compares the situation of, let's see, of this strong matrix of matrices. This is a matrix of matrices. These values that, as you could see here, are different depending on the neighbors, to a kind of null hypothesis transition spatial Markov chain. Okay, so the system, the test computes an initial transition Markov chain matrix and compares the results with these results. And if the results, the real results, differ a lot from this result that represent the null, is when the test will go up. So the test, the math of the test, is awful, Sometimes it is terrible. So if you are not a statistician, a theoretical statistician, and I must recognize that I am not, what I recommend you, and I do, is analyzing the test in depth and knowing how it works. And this is the way it works. It computes a transition, a first transition that is considered as, I know perhaps it is random, and this kind of transition that considers, it is considered like the null, is visioned against all these ones. And if the real result departs a lot from the null transition matrix, the test will go up and you will reject the null, because the value of the test will be much higher than the critical value, as you should know from statistics. Okay, and so it is interesting. In our case, we rejected the null, and what we concluded is oh, sorry. No, this is also oh my God, this is a typo. No. We could say it does depend. It is really very, very significant. So the Chilean city growth in one moment of time does depend on average population of neighboring cities in previous period. Well, I will give you, because I must finish also these slides, because I'm not sure if we will have time to finish. So don't worry, because I'm going to test and correct everything. So since I reject the null was independence as in time series, okay? So I reject the null, so I have a spatial dependence. So city growth from one period to the next period depends on the neighbors in the first period. So having neighbors in the first period will condition the evolution to the future of one spatial unit. This is the way. So we are considering growth for jumps up or down, okay? And the neighbors are at the initial time. So the neighbors at the initial time are very important. This happens with income per capita. So I could check it. For instance, for Spain, it was very clear. So it is not the same if you have richer neighbors than if your neighbors are very poor. Of course, if your neighbors are rich, Sometimes you will receive some presents, or they are going to be generous with you, or it is always much better than having poorer ones. I'm talking as if I was considering only individual elements, but it also works for regions, because I checked this property for our provinces, and this was clearly significant. So for income growth in our country, it is very important be closer to the main economic centers. So in this case, you cannot move. If you live in a province that is very isolated and poor, surrounded by poorer ones, people can move, but not the region. Okay, and sometimes it's a problem. So how creating wealth in around a place or in a place when it is surrounded by a desert? It is not easy. As you know, it's a big challenge everywhere. And okay, the ergodic distributions also are important here. As you can see, for each class, so the first quintile, the second quintile, so small towns, town, city, big city, and megalopolis, I can compute one ergodic distribution. So one if the neighbors are in average small towns, if the neighbors are in average towns, if they are cities, big cities, or megalopolis in terms of population. And what we found was very interesting. So these distributions for neighboring cities of a small or a small to medium size. So these ones that I highlighted here are left skewed. So left skewed in what sense? In the sense that the higher probabilities are, as I said, more or less concentrated in a small to medium size, okay? And not in the megalopolis or in big cities. And what is the interpretation of this outcome? So in this outcome, the information that gives us is that you have higher probability than a city will shrink and become a smaller town in the long run. Not a megalopolis, no, but a city, even a small city, but particularly a city or a town, the probability of going down, if they are surrounded by smaller enclaves, okay, as neighbors, the probability of losing population in future, because this is in the long run, so it is in the very future, okay, the probability is losing more population. So being in the last term, in the last moment of time, in the very future, as I said, being so small that they could disappear. In the infinity, they will disappear, or they tend to disappear. But what happened with the largest neighboring cities? So if they are surrounded by also larger cities, when they are a big city surrounded by large cities, it is a right skewed. So the probability of going up or staying being large cities is the highest, what implies a long-term concentration process. So what would we expect for Chile in the end of the times, in the very future, in the long run, that big, not only cities, but big metropolitan areas, because they are surrounded by very big, so they will increase, boom, 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 okay? And the small ones, they will tend to disappear. So deserts versus very small, very large metropolis, or what we could call metropolitan areas, so groups of very big cities, concentrated, very close, one to another. So the country, the population will migrate. This is what will happen. They will migrate. They will concentrate around the megalopolises or the large cities, and they will create like the certain tremendous areas that will be very populated, largely populated, and some others will more or less disappear. Not completely, but more or less disappear. So this is challenging also for politicians and in Chile, and this is a challenge, as I said, to revert this process. So this process is terrible because it is very uneven, and it will create inequalities for sure, of course, and it is not desirable. So having this kind of empty spaces, it is something that worries us a lot in Spain too. So this empty Spain versus the full Spain, we are more or less experiencing something similar, and so it is not desirable. Okay. Let's go to the LISA, or the local indicator of spatial association. But the LISA that is connected with the Markov chain. Okay. Let's stop because today we will have 2 hours of class. So let's stop 5 minutes, and I will be here in 5 minutes. Okay. What I'm going to do is stopping recording, and oh no, stop recording. Okay.